talking about how you can choose an FPGA for your design. I'm not going to tell you which FPGA you should use, but I'm going to tell you how to go through the trade study of picking an FPGA. So a trade study, for those of you who have never heard that term before, is a study where you look at all the requirements for your project, you find all the solutions that satisfy your requirements, and then you weigh your requirements by importance. So if the most important thing is cost, that might make some choices be more appealing than others. If the most important requirement is a temperature requirement or a speed requirement or resources, you need to make that determination, and that's what's going to lead you to down select to an FPGA. So you will choose one FPGA at the end of all this whole thing. So let's look at what your requirements might look like. You might have I/O count requirements, input-output count, so how many pins there are physically on the device, how many resources there are on the device. I'm going to give a brief list here, and then I'm going to go into each one of these with a little more detail. So resources are like flip-flops, your DSP multipliers, your blockrams, things like that. How fast it can operate at, the temperature at which it can operate, how much power it draws, any hard IP, intellectual property. I'll go into what the details of that are, some examples, how much it costs, and maybe you have some vendor preferences. If you have a really good Xilinx rep in the area, maybe that's something to tilt the scales in their favor. So let's get into each one of these. First of all, I/O count. This one I think is the easiest requirement to figure out for your needs. It's basically how many pins do you need? How much stuff do you need to connect to external to the FPGA? Is there anything that's specialized or reserved that you need to hook up to? So for example, SD-RAM, DDR2, DDR3, things like that, LPDDR, low power DDR, external memory, things like that. Do you need to reserve any special pins for those kinds of things? And one piece of advice that I would give in this situation is run a basic place and route before you purchase your PCB, before you purchase your physical design printed circuit board. Run a super basic place and route that just makes sure that your clock input pins, there's special pins on an FPGA that are reserved for clock inputs. Just make sure that you correctly assigned the clocks to be on those pins and that that's able to drive flip-flops, and your SD-RAM is properly wired up. You don't have to run it and make sure that it's working correctly necessarily, but just to make sure that the general place and route is correct. And the more complicated your design is, the more I emphasize this. If you have a really simple design, it's less important, but if you have like SerDes, which are like high-speed serial deserializer transceivers, if you have SD memory, if you have really fast I/O, those are things you really want to test out before you purchase your printed circuit board to make sure that you're actually choosing the right FPGA for your needs. Next, resources. This is the one that gets probably the most attention when people decide which FPGA development board they want to play with, for example. It's what can you do with your board? What can you do on your FPGA? How many flip-flops and lookup tables do you have access to? And this is really something that beginners struggle with, and it takes a long time to get comfortable with, oh, I think that's going to be 500 flip-flops, or I think this particular module is going to take about 1,000 registers. And that's something that you'll just get better with as time goes on. If you have no idea whatsoever how many resources things are going to take, try to create a test project if possible. And if you just run through synthesis by itself will tell you, you don't need to pin out your design, but it'll tell you how many flip-flops and how many lookup tables your VHDL or Verilog code uses for whatever design you choose. That's something, it's tough, but I will give a suggestion later on, which is that you might want to purchase the largest FPGA in your package so that you can always go down. I'll talk about that later on. Blockrams. Blockrams are used for FIFOs, dual port memories, and ROMs for the most part. I have a whole other video on blockrams and another video on FIFOs. So if you're wanting to learn more about those, you can check out that video. But that's another thing that you might want to weigh. Count up. I definitely recommend counting up how many FIFOs you think you're going to have, how many dual port memories you're going to have, to make sure that you have enough blockrams. Because if you run out of blockrams, that's a big problem. And then DSP tiles, digital signal processing, are mostly used for multiplies and adds. So any fast multiply or add operations that you have that require hard physical components, those are going to be pushed into the DSP tiles on your FPGA. So again, that kind of depends on what you're going for, what you're doing. But those are the big resources trades that you can make. Operating frequency. In general, things that run faster cost more money, so there's a trade-off there. Couple rule of thumbs here for people who have never had to deal with this. Anything under 100 megahertz, usually whatever FPGA you choose, you're going to have not a lot of problems with. Maybe on the really low end, that might be pretty fast, but anything in the mid-range under 100 megahertz is no problem. I would say that over 200 megahertz is where you start needing to be careful with your design and maybe choose something that's extra fast, and maybe start doing, if you have to run any logic over 200 megahertz, you might want to really run through place and route before purchasing your design to make sure that it's going to work correctly. Unless there's some hard IP that runs at that speed, like guaranteed for that speed, that's going to be okay. But any like soft IP flip-flops and lookup tables that run over 200 megahertz, something to be careful with. I've run things faster than 200 megahertz with no problems. You just need to be careful. And then different speed grades exist for one FPGA package. So usually that's like a -3, -2, -1. Those are the different speed grades. -3 is usually the fastest, 2 is the mid-range, 1 is the slowest. And you can look at the individual data sheets for each one of those speed grades to see how fast things run. What the vendors do is they'll produce a whole slew of FPGAs, and they'll bin them. They'll run them all and figure out which ones are the fastest. There's like a Gaussian curve, right? The really fast ones are the top third of the designs, and those go into one bin, and the medium range ones, they go into another bin, and the low range ones, they go into another bin. And those are the different speed grades. So you pay more for a faster FPGA if you need it. One thing I was saying before was that you can always buy the fastest speed grade, the one with the highest registers and flip-flops, and you can always go down. So you can always start with like a -3 in one particular package and then go to a -1, and that might be fast enough for your design. The -1s usually cost less. One recommendation I have is to check the I/O speed on a data sheet. So make sure that your I/O, your input-output, can operate at the speed you want it to operate at. I had a problem once where I was trying to run a pin, it was like a DDR pin, at a frequency that was higher than the FPGA recommended. And it's not easy to deal with that. So make sure that you pick an FPGA that can run the I/O at whatever speeds you need. Temperature. This, for the majority of you, is not going to be a problem, but it is something to trade. I mean, I worked in the defense industry in the United States for a long time, so I was always in industrial, automotive, or military temperature ranges. And military especially is hard to find parts for because it's such a huge range of temperatures, -55°C to 125°C, and -55°C is extremely cold, so that's hard, and that's expensive. Commercial is where probably the majority of you are going to be, and that's standard 0°C to 85°C. That's operational range. The storage temperatures can be a little bit wider, and I don't know them off the top of my head, but you can look that up as well. Something to trade. The only difference here is when the further down you go on this table, the harder it is to get parts, and the more expensive it is to get parts. So commercial, if you can deal with that, is cheap and easy to get. Power. Power is important for some people. Power might not be a problem for you at all. Power might be the #1 requirement for you. I worked for a company where we made handheld products that ran off of AA batteries, and power was probably the #1 requirement. So it totally depends on what you need. Does your design run off batteries? Does it need to last for a long time? Power might be super important. Another reason why power is important is if heat's going to be a problem. And heat can usually it shouldn't be ignored. Always pay attention to heat. Because if you have an FPGA design that's this big and it's dissipating 1 watt and you're not heat seeking it, something the size of a postage stamp, if you don't put a heat sink on top of that, it's going to get really, really toasty, and you might destroy your FPGA. Something to be careful of. Now, most FPGA designs, that's not going to be a problem. But if you have something really demanding in a really small package, then that could be an issue. In general, the tools have good power estimators. So you can get a pretty good feel for how much power your design is going to take by running through the power estimator tool. You got to tell it your clock speed, how many resources you're using, flip-flops and block grams, and whether or not you're using external interfaces. That's the other big contributor to power. So if you have like a DDR interface to hook up to external memory for your FPGA design, that's going to take a lot of power. SerDes, high-speed serialization, deserialization takes a lot of power. If you don't know what I'm talking about, don't worry about it. You don't have to worry about it. There's a lot to trade, in case you haven't figured that out. So some of this doesn't apply to you. Some of it applies to, some of this is really, the more things that apply, the harder the trade is to make. So hard IP, hard intellectual property, SDRAM interfaces, DDR2, DDR3, those are usually built into the fabric of the FPGA, and those usually have pins that are reserved, so you need to block off a section of pins that are dedicated to running a DDR2 interface or a DDR3 interface. That's, if you need hard IP, that's an easy one. You just don't choose anything that doesn't have a DDR2 interface, for example. A built-in microcontroller. So a lot of FPGAs have a built-in hard IP processor inside of them, and if that's a requirement for you, whether or not that's a requirement, you'll probably know. And I don't. There's pros and cons to using a built-in microcontroller, and that's probably a subject for another video, why you might want to choose something like that. But if you need one, definitely look for FPGAs that have that. SerDes, high-speed serialization, deserialization, that's basically if you've never heard of that before, it's like connecting to anything that runs at above 5, maybe a gigabit per second. So it's dedicated serial fast lines to send and receive data. So that's used in things like PCI Express. It's used in high-speed video communications. Things like that is when SerDes is used. Make sure these pins aren't double counted. So if you have to reserve pins for one of these hard IP blocks, make sure you don't accidentally say that it's available somewhere else. Just a warning. Cost is, it's interesting. Cost is something I haven't really been susceptible to. I've always had budgets that are just whatever it costs, doesn't matter. But I'm sure a lot of people have cost is pretty important. So how much can you afford? What does the whole unit cost need to be? And does an FPGA, ask this question, does an FPGA make sense for your particular design? FPGAs usually have a higher cost than a microcontroller, for example. Microcontrollers are a dime a dozen, and they're everywhere, so they're a little bit cheaper. So if ask the question, does an FPGA make sense? They're more expensive. The cheapest FPGA you can get is a few dollars, but you can get some that are hundreds, if not thousands of dollars. I mean, the high-end ones are really expensive. So transition to that, let's talk about vendors. So the 4 main vendors that I am most commonly familiar with, Xilinx and Altera are the 2 big guys. And actually, Altera was bought by Intel a little while ago. So now it's really Xilinx and Intel are the big ones. And then the 2 medium, small-sized guys duking it out are Lattice and Microsemi. And Microsemi was previously Atmel. And they're all different. If you have any, I don't particularly feel any strong affinity towards one or the other. I think the other requirements are more important, and they all the vendors behave similarly. So the only reason, if you have like a really good rep who can answer a lot of questions, like a technical support person in your area who can help you out with technical things, maybe that might tip the scales towards one or the other. But in general, I'm not like, oh, you have to use Xilinx all the time. That's the only way to go. As a matter of fact, for the Go board, I chose Lattice because my number 1 requirement for my design, when I designed the Go board, was make it cheap. I know that people don't want to spend a lot of money on a little development board they're trying to get familiar with. They want to see if FPGAs are right for them. So I went to the cheapest vendor I could find, and that's Lattice. So I'll talk a little bit more about how I chose the FPGA for that. So big and fast, those are going to be Xilinx and Intel. If you need something to run as much data as possible, as quickly as possible, you're going to go to those guys. If you want to get small, cheap, go to Lattice. If you want to do somewhere in the middle, there's a whole bunch of FPGAs in the middle. So the middle is probably the hardest to really narrow down. And there's a couple miscellaneous things. Boot times. Boot times, there's two different types of FPGAs. There's flash-based FPGAs, which are rarer. Let's see. Microsemi makes flash-based FPGAs. Lattice makes flash-based. I think the Intel Max 10 is flash-based, but don't quote me on that. But SRAM-based is a lot more common. The difference here is that the flash-based ones are quick to boot up. That's one thing they have going for them. SRAM-based are slower boot times. If you need to go into space and you have to worry about radiation, I work in the space industry and I need to worry about radiation. So that's something I need to pay attention to. Most of you don't. Physically, the size of it, how big is it? So is it, and that can relate to the package too. So is it a BGA, ball grid array, or is it a TQFP, top quad flat pack, which has pins coming off of it? And how big is it physically? How much board area do you have? That could be actually really important if size in space is a limiting factor. And then ball pitch too. I figured I'd mention that. Ball pitch is the width in millimeters between two balls on a BGA, ball grid array, FPGA. Some ball pitches are really small, like 0.3 millimeters, 0.4 millimeters, and some board houses that make that PCB, printed circuit board, have a hard time with small ball pitches. I think everybody at this point can handle 0.5 millimeters and up with no problem. There was a point in my career not that long ago where 0.5 millimeters was like, oh, only a few people can do that. But I think that the PCB technology has gotten better, so that's become less of a problem. So in conclusion, I would say the most common things to focus on: your input-output count, the resources that you have, which again is difficult for a beginner to get a handle on, and I would say cost. I personally haven't been subjected to that too often, but I think most people probably are. You probably want to keep the design cheap. And my recommendation is, for your first spin of a printed circuit board, buy the biggest and fastest FPGA in a package size, and you can always go down. So that -3 that I mentioned, that's the fastest one. If you find that you can run at a -1, then when you go to purchase 100 boards or 1,000 boards, whatever it is, you can always choose the -1 later on. When you're doing your prototyping, you don't want to limit yourself artificially. And same thing with resources. You can get the biggest one in that particular package, and I'm going to show you that in a second. And then you can always say, like, oh, I only used half of it. I only used half of my total resources available, so I'm going to go to the next smallest resources in that particular package. And every vendor has some sort of product table or selector guide that'll weigh all of these things for you and try to tell you why their FPGA is the best. It's the lowest power, it's the cheapest, it's the fastest, everything like that. So here's one for Lattice, and I'm going to talk about Lattice because that's the one I used for the Go board. So I chose, again, something that was cheap. So I looked on websites to figure out what could I get for the lowest cost possible, because I wanted you guys to be able to have fun using the nanland.com Go board, but I didn't want to break the bank. A lot of boards are like $100 plus for a development board. I wanted to be significantly under that, so that was my main requirement. And inside of Lattice, there's this ICE40 series. The other nice thing about the ICE40 series is that it's someone reverse engineered it, so it's completely there's open source tools that you can use to synthesize and place and route your Verilog design, which is pretty nice. So I chose the HX1K. It comes with 1280 logic cells. It comes with, gives you an estimate of how much power you're going to use, how much block RAM you have available to you. And inside the HX1K, there's a couple different choices for So I guess I should say this. Inside of each package, here's the pitch right here, 0.5 millimeter pitch, which I think most people can handle. And there's 3 different packages. There's a 132 ball, it's a BGA. It's an 8x8 millimeter, so that's pretty small. And you can get the 1K, which has 1280 logic cells. You can get the 4K, which has 3520 logic cells, or the 8K, which is 7680. So if you don't know how many resources you need, I would recommend starting with like the 8K if you're building your own board, for example, and you can always go down. That's the nice thing. So these are, this is the most expensive one up here, and then the 1K is going to be less expensive. But the nice thing is that this package, the 132 ball, is supported in all different densities. So that's kind of nice. For the Go board, I chose this one right here, the VQFP 14x14, because it was small. 100 pins satisfied my needs. So that's what's on the nanland.com Go board. So that's it for how to trade your FPGA and how to choose one for your needs. I hope that was informative. I hope it helps to figure out the different things you might need to look at when you're choosing an FPGA for your own designs. Some requirements are more important than others, and that totally depends on whatever project you're working on. It's something you get better with at time, so spend some time up front getting familiar with all the different vendors and looking at their different products, and maybe talking to people too. They'll help you out. So I appreciate you guys watching. Hope this video was helpful. If you want to support this YouTube channel, please consider purchasing yourself my development board, the nanland.com Go board. I think it's great, and I think you're going to have a great time learning all about FPGAs. I have tons of tutorials on YouTube, so subscribe to my channel, get yourself a Go board, and start digging into VHDL and Verilog, and/or. It doesn't matter. Thanks. Bye.